In 2023, a remotely operated vehicle descending into the Challenger Deep, the deepest surveyed point on Earth, captured footage of something that was not supposed to be there. Not a known species, not a catalogued organism. Something that forced the research team to go quiet for 3 days before issuing a carefully worded statement that said almost nothing at all. The Mariana Trench has a way of doing that to people, making them careful, making them reconsider what they thought they understood. And if there is one thing this video will prove beyond any reasonable doubt, it is that almost everything you were taught about the deepest place on the planet is incomplete, outdated, or quietly, significantly wrong. 10,900 meters is a number that barely registers until you try to picture it. The Challenger. Deep is not just the deepest point in the ocean. It is a place so far removed from ordinary experience that the usual comparisons fail. Imagine Mount Everest, the highest peak on Earth, inverted and dropped into the trench. Its summit would still sit more than 2 kilometers beneath the surface, lost in darkness and cold. At this depth, the pressure mounts to 1,086 atmospheres, over 1,000 times what you feel at sea level. Every square inch is burdened by more than 15,000 pounds of force. The steel hulls of ships, the glass of submersible viewports, even the molecular bonds in plastics and ceramics are not immune. Only the most carefully engineered spheres of titanium, forged and tested to the edge of failure, can survive the descent. The Challenger Deep is a place where the limits of human invention are tested as ruthlessly as the limits of biology. The scale is not just vertical, but existential. More people have walked on the moon than have visited this trench. While lunar footprints endure in dust, the bottom of the Mariana is a shifting, unmapped world. We have mapped the surface of Mars in greater detail than this abyss on our own planet. What lies beneath those final 2 kilometers of water above Everest's peak is not just a question of depth, but of survival. The pressure here can collapse a submarine hull in milliseconds. For any living thing, every cell and chemical bond must be built to resist a force that would crush the unprotected instantly. The trench is not merely deep, it is a frontier where the rules of the familiar world no longer apply, and where the unknown is measured not just in meters, but in the limits of what humans can build and what life can endure. Life in the Mariana Trench does not cling to existence on the edge of extinction. It thrives, rewriting the rules. Sunlight never reaches these depths, yet the sea floor is not barren. Instead, it is home to entire ecosystems powered not by the sun, but by chemical reactions. Here, chemosynthetic microbes form the foundation of the food web. These bacteria use hydrogen sulfide and methane, leaking from the crust or produced by decaying organic matter as their energy source. They oxidize these chemicals to create organic carbon, fueling a slow-motion cascade of life in the darkness. Among the most remarkable survivors is Hierondelia gigas, a species of amphipod that scours the trench floor for nourishment. Its genome reveals a toolkit of pressure-resistant enzymes, allowing it to break down detritus and even digest wood that sinks from the surface. These amphipods are not isolated freaks. They represent a lineage that has adapted to the crushing force and cold of the Hadal zone over millions of years. Some populations show genetic divergence between trenches, but all share the same suite of molecular tricks for surviving where most life would be destroyed. Chemosynthetic mats coat outcrops and sediment, providing food for amphipods, polychaetes, and the occasional snailfish. Even the mud is alive, packed with microbial communities that fix carbon and cycle nutrients. At these depths, every scrap of energy is precious. Nothing is wasted. The trench is not a dead end, but a living laboratory, where evolution has found ways to flourish in a world without light. The true wonder is not that life survives here, but that it has found so many ways to succeed. At the bottom of the Mariana Trench, the ground beneath the submersible is anything but stable. The Pacific Plate is sliding under the Philippine Sea Plate at a rate of about 5 centimeters per year. A slow-motion collision that carves the trench deeper and triggers constant upheaval. Down here, the seafloor is not a silent plain. It is a battleground of shifting mud, fractured rock, and sudden violence. Micro-earthquakes ripple through the region every day. In 1993, a magnitude 8 tremor rocked the trench, sending shockwaves through the water column and dislodging vast volumes of sediment. The scars of these events are written across the landscape. Fresh, slump scars, turbid plumes, and layers of displaced mud that bury anything in their path. Radiocarbon dating of sediment cores reveals landslides that have swept the trench floor again and again, sometimes triggered by the very tectonic forces that shaped the basin. For robotic explorers and crewed submersibles, this instability is more than a scientific curiosity. It is a direct threat. Tethers can snag on debris from recent slope failures. A sudden slide can cloud the water with silt, blinding cameras and sensors, or even trap a vehicle in a shifting mass of mud. In 2003, the Japanese ROV Kaiko was lost after a storm disturbed the trench wall, tangling its cable and cutting off contact forever. Even in calmer years, teams report abrupt turbulence and unexplained bursts of current, signatures of sediment slumping in real time. Every descent is a calculated risk, with pilots monitoring for tremors and ready to abort if the ground begins to move. The bottom of the trench is not a static abyss, but a place of relentless change, where the forces that built the planet are still at work. This makes every attempt to map, sample, or even observe the seafloor a race against the next unpredictable upheaval. Mapping the Mariana Trench is still an exercise in uncertainty. Only about 5% of its seafloor has been charted with modern multi-beam sonar, detailed enough to reveal features smaller than a city block. The rest is rendered as rough grids, where a single pixel can hide entire mountain ranges. Most existing maps rely on single beam soundings, isolated depth readings spaced kilometers apart, then smoothed into a surface that erases the trench's jagged reality. Satellite altimetry, often used to fill gaps in ocean mapping, fares even worse here. Its resolution rarely exceeds 10 kilometers, missing the narrow canyons and steep slopes that define the trench. The Seabed 2030 project, aiming for a complete ocean map, reports that Challenger Deep's best available grids are no sharper than 1970s radar images. In some areas, a football stadium could disappear in the data. Vast sections remain unsurveyed, leaving the trench's true shape and its anomalies hidden in statistical shadows. Speculation thrives in the abyss, fed by the grainy outlines and fleeting shadows in deep-sea footage. Stories circulate of creatures so vast and alien that they seem to belong to another world. A world where the laws of biology are suspended and the improbable becomes possible. But every living thing, no matter how strange, is bound by one inescapable rule: energy. The carbon budget of the Challenger Deep is not a matter of belief, but of arithmetic. At these depths, the rain of organic matter from above dwindles to a trickle. On average, less than half a gram of carbon lands on each square meter of the trench floor per day. Most of that is scavenged by amphipods, worms, and microbes, with only a sliver left for anything higher in the food chain. When ecologists run the numbers, the verdict is clear. The total energy available cannot support a population of large, active predators. A meter-long animal would need more carbon than the entire square meter beneath it can provide, even in the richest patches. The rare chemosynthetic oases, vent fields that leak methane or hydrogen sulfide, are too scattered and too small to overturn the math. The result is a world where life is abundant, but not gigantic. The greatest mysteries of the trench are not monsters lurking in the dark, but the ingenuity of survival itself. How life, with so little, can persist at all. The evidence leaves wonder intact, but it trades fantasy for the far more astonishing reality of a food web balanced on the edge of physics and chemistry. Over half a century after the first descent, the bottom of the Mariana Trench remains a destination for only a handful of people. Fewer than 15 individuals have made the journey to Challenger Deep, while 12 astronauts have walked on the moon. This is not a quirk of history, but a measure of the trench's resistance to human presence. Each dive is a logistical feat, requiring a vessel engineered to survive pressures exceeding 1,000 atmospheres, forces that would instantly collapse ordinary materials. The comparison with lunar exploration is not just numerical. On the moon, radio signals travel at light speed, with no interference. At the bottom of the trench, communication is forced through kilometers of dense water, relying on slow acoustic transmissions that garble and delay every word. Data from each dive is not broadcast live, but reviewed in careful stages, often held under embargo, until every anomaly is checked and every artifact is explained. The reason is simple. A single, ambiguous image can ignite a storm of speculation, and science moves at the pace of verification, not sensation. In this world, the unknown is not just a gap in knowledge. It is a boundary guarded by caution, patience, and the hard lessons of the deep. Sinking Mount Everest into the Challenger Deep still leaves it submerged beneath pressure over 1,000 times what crushes us at sea level. We have explored less of this abyss than the surface of Mars. 12 people have walked on the moon. Fewer have seen this world. Some frontiers remain defiantly, impossibly real.